A very good morning, students. In today's lecture, let us look at the sustainable infrastructure development and what role the natural geosynthetics can play in this development. Well, before we go into the sustainability and how the geosynthetics can help in the sustainability, let us look at what is sustainability. The dictionary meaning is very simple. Any activity that enables the future generations to enjoy whatever we are enjoying now in terms of the natural resources or the fresh air or the fresh water is called as sustainability or sustainable activity, because we are not utilizing the natural resources or destroying the nature so much. And so the now in this context we can see how the geosynthetics can play a role in sustainable infrastructural development, because the world is expanding so fast and especially India is developing so fast that we are building thousands and thousands of kilometers of roads and railway networks, and we should be able to reduce the utilization of natural materials, so that our dependence or the sustainability of the future generations is ensured. And the sustainability, especially in the context of India, should also include the aspects related to the economic opportunities that are provided for rural and semi-skilled people, because if we bring in very hi-fi equipments that displaces all the people and we do not make use of the human resources that we have in our rural areas, then that is also not good, because they will not have any employment, they will not have any economic opportunities. So, in that context, both the geosynthetics and also the natural geosynthetics can play a very important role in the sustainability. And let us look at some aspects of how the geosynthetics can play a role in the sustainability. Well, in all aspects of construction and the sustainability, the geosynthetics can play a role, and the geosynthetics, we have seen that they can be used to reduce the consumption of natural construction materials like aggregate, soil and other materials, and in the long run because of that our activities become more sustainable. And these geosynthetics promote the use of local available soil or marginal soils, and the carbon footprint of most highway projects can be reduced by the use of geosynthetics. And this aspect we have seen a few lectures back on how the carbon footprint can be reduced by reducing the transport of aggregate and other materials. And of course, these natural geosynthetics, they help in rural employment, because that is one of the cornerstones of any national development. Well, let us look at how a geotextile performs when it is placed below a road base. It could act as an agent for fluid transmission, that is for drainage purposes. It can act as a filter to prevent piping, and another picture of the same filter. Then it can act as a good separator to separate out the aggregate from the subgrade soil, and it can act as a protector to prevent or to reduce the surface erosion. And also these geotextiles, if they are very stiff, they can also act as reinforcement materials. Well, in the context of applications, the natural textiles or the natural geotextiles, they tend to be much thicker as compared to their polymeric counterparts, and that could in a way give us some advantage, and that is illustrated here. So, when you have a very stiff thin geotextile, you require a large depression or the large rutting to develop sufficient tensile force to counteract the applied loads. And if you have a thicker textile or a thicker reinforcement material, we require smaller rutting to develop similar order of the tensile force. And if we have even thicker geotextile, we require very small rutting to mobilize the required amount of tensile force to counteract the applied forces. So, that means that the natural geotextiles, if they are very thick, they can be made to promote the required tensile forces to counteract our applied forces. And let us go back to the different functions that are given by the International Geosynthetics Society. This we have seen in one of the earlier lectures. These geosynthetics can play important role in most of the constructions. They can act as a barrier, and the barrier function is exclusively reserved for geomembranes, and this is one activity where our natural geosynthetics cannot play a role. And the drainage applications, these natural geosynthetics can play a very important role, because the thickness of the coir and jute geotextiles is much more than that of synthetic fabrics, and so they can act as good drainage layers. And in the surface erosion control, the natural geotextiles and other products, they play a very important role. And filtration, it is it all depends on the pore size of these textiles, and the natural geotextiles can also be fabricated to have a desired pore opening size. And protection of the geomembranes, the natural geotextiles can play a good role because of their thickness and their impact absorption capacity. And to some limited extent, the natural geosynthetics can also play a role as a reinforcement layer and also as a separator, depending on the type of loads that we deal with. And here we see one innovative application of the geosynthetics for coastal erosion protection. Here this breakwater was made entirely by using the beach sand. The beach sand was filled in these geotextile bags, which are in turn placed inside a rope net gabion, and everything is tied together to form the breakwater units. And if it were not for beach sand, we need to import large boulders, and that is the typical solution that is adopted at most of the Indian coastal protection systems. We just simply bring the large boulders and dump them to counteract the erosive forces. But here we can use the abundantly available local beach sand itself to construct our structures, and this is one application that is sustainable, because we are not really destroying any natural resources in this construction. Well, one advantage that we have with these natural geosynthetics is evident from this statement that I have taken from one of the papers written by Mr. Sanyal of the Jute board. During the 100 days of the growth of the jute plants, per 1 hectare, the jute plants can absorb about 15 metric tons of carbon dioxide and release about 11 metric tons of oxygen into the atmosphere, and this is a very clear evidence of the advantage of the vegetation, of course, all the plants, they absorb carbon dioxide and release oxygen as part of their natural process, and the jute has more capacity to do this, and the coir fibers that we use for making coir geotextiles or coir ropes, these are entirely derived from the husk of coconut fruit by retting process, and it is mostly done by semi skilled and manual labor. Both the jute processing and the coir processing is a labor intensive, and it provides lot of employment for the rural people. See, one question that we need to ask ourselves is, our natural geosynthetics like the jute and the coir, they have a limited life. They cannot stay in the soil forever, like unlike our synthetic counterparts like the geogrids and geotextiles made of say polyester or polypropylene or polyethylene. They can last for hundreds of years without any degradation, whereas the natural geosynthetics, they have a limited life, and various studies, they have shown that they can safely stay in the ground for about 4 to 6 years depending on the soil environment and the type of material, whether it is coir, jute, hessian and so along. And how long do we need the support from geosynthetics that are placed? It depends on the application. So, if it is a below ground application like a ground improvement project or something, we may require them for about say 1.5 to 2 years until our the clay soil consolidates, or if it is a road base, maybe for about 2 or 3 years until the subgrade gains the strength, or in some other application or in erosion control, we require the protection of the surface only for about 1 or 2 seasons until the vegetation takes root. Whereas in some constructions like steep retaining walls or embankments, the requirement of the reinforcement is permanent. That means that as long as the structure is existing, we require the reinforcement to provide the reaction force, and in such applications the natural geosynthetics may not play much role, but in all other applications where the need for the geosynthetic is limited, we can employ our natural geosynthetics very easily. Well, what are the different types of fibers that we have for fabricating our geotextiles and geogrids? These natural fibers, they can be of they can have the origin of vegetative matter or animals or mineral origin, and vegetable fibers, these are extracted from the fruits of plants, and these are light and hairy, and some examples are the coir and the cotton fibers, and the bast fibers, these are found in the stems of the plants that provide the strength to the plants, and usually they run across the entire length of the stem and are therefore quite long. And some examples of the bast fibers are the hemp and the jute, and the bast fibers, they are very long because they run along the entire trunk of the tree. And there are also leaf fibers. Some examples are the pineapple, banana, palmyra, sisal, and these are generally rather rough and sturdy, and they can be used for several applications. The palmyra leaves, they are used right from the ancient days in India for writing our scripts and for other purposes, writing purposes. And the other type of fibers that we have, mineral fibers, asbestos, sorry, there is a spelling mistake, and animal fibers, wool and silk. The coir and jute, they are very important for the Indian economy because India is the largest producer of both coir and jute, and the coir fiber itself is obtained from the coconut, by defibrine operations, and the fiber is extracted from coconut husk either by retting or by mechanical crushing and then decorting process. And the coir fiber can have lengths anywhere from 5 to 30 centimeters and diameter 0.2 to 0.8 millimeters, and the entire process is shown here. The coir fiber is obtained from coconuts, and this is looks like this. This husk surrounding the coconut fruit is the one that that gives us the coir, and it is mechanically the husk is removed, and then by soaking in water, that we call as a retting process, for about 6 months to 1 year period, the fibers separate out, and then by some mechanical and labor intensive process, the fiber is separated, and then it is made into textiles and ropes like this. So actually we can feed the individual fibers and spin them into coir ropes and nets, and here we see a needle punching machine that is producing coir geotextiles. And the Indian coir industry is quite large, largest of its kind in the world, and the coconut is under cultivation in about 5 million hectares of land, and the annual production of coconuts is about 12,600 millions, largest in the world. About 35% of the husk is utilized, and the production of coir fiber is approximately 369,000 metric tons, and it employs nearly 600,000 workers, and 80% of these workers are women, because it is a labor intensive process and it does not require much of a skill. And the coir is exported to more than 80 countries, mostly in the raw form, and just as how we are exporting the minerals, we are also exporting raw coconut fibers that are converted into useful products. And the basic composition of these lignocellulosic fibers, that is the fibers that have lot of lignin and cellulose content. The cotton has very high cellulose content, 92 to 95%, then lignin is 0. Then let us look at jute. Jute also has a very high cellulose content, 59 to 71%, lignin is very low, and the coir has got a lower cellulose content and higher lignin content, 41 to 45%, and higher cellulose content gives the fibers more flexibility. So the cotton and jute, they are more flexible and more smoother as compared to coir, and at the same time lignin gives them the life or the durability when it is exposed to soil or water or other environmental factors. So comparatively the coir has a longer lifespan, but lesser workability because it has a lesser cellulose content. And the coir and the jute, they can be employed for several applications, and here we see some products made for use in the pre-consolidation of soils, the PVDs, prefabricated vertical drains. Here we see a PVD made of jute and coir. Is actually the coir wick is there that can transmit water, and the jute filter cloth is surrounding this the drainage core to act as a filter. And here we see another example of very large diameter coir rope that can act as a wick, that is surrounded by a textile made of jute or coir that can act as a filter. And there were quite a few studies on applying these PVDs for pre-consolidation, and pre-consolidation is normally designed to consolidate the soil within about 1.5 to 2 years, and for such applications the natural products, they were shown to be excellent. And some of the different coir products, we can have nets or we can have a textile. This is a coca log, this is a non-woven textile, and this is a prefabricated vertical drain. Coca log is one of the more recent product. It's made in the form of a log. This entire log is made of coconut fiber and non-woven or woven geotextile, and it floats in water, and it can be employed in this schematic manner for river bank protection. If we provide it along the length of the river bank, because of their flexible nature, they can take the shape of the river bank and absorb the wave forces or water forces, and the main advantage is they can promote the growth of vegetation through them, and so in no time, because of the mulching action of this coir fibers, and because they promote a good microorganism for the vegetation of plants, the vegetation takes root, and once the vegetation takes root, we can solve most of the erosion problems. And another innovative application that we can think of is in the formwork for the concrete. See, these geotextiles, here we see one application of a coir geotextile. The coir and the jute geotextiles, they can help in moisture control. They can stabilize the moisture content along the edges of this. See, the coir geotextiles, they can distribute the moisture content so that the curing process of the concrete is good. These are called as permeable formworks, and it is catching up very fast all over the world. See, most of these natural fibers, they have a very good water holding capacity, and the coir can absorb about almost 100% water if it is immersed in water for about 24 hours. The jute, they can absorb about 12 to 14% water by their weight, and this property of the water holding capacity is good because they can provide moisture for the growth of plants when we employ the natural fabrics for erosion control applications. And another advantage that we have with natural fibers is their mulching properties. Mulching is gradually they undergo the biological degradation, and they produce some nutrients for the growth of vegetation, and some example applications are shown here. This is a typical seen on most of the highway and the railway embankments. Because of the flow of rainwater, we have lot of gullies formed, mainly because there is nothing to hold the soil together. If there is a good vegetation, the roots of the vegetation can hold the soil together and prevent the erosion, and we can control the erosion by promoting the vegetation growth. And here we see one coir carpet that is impregnated with seeds, and it comes in the form of a carpet. You just simply bring it and roll it on the area that you want to treat, and this is the scene of one steep embankment that is grown with a lot of vegetation, and here we can see one of the exposed coir geotextile, and within about 1 to 2 seasons the vegetation grows, and it takes a good root in the soil, and that prevents the surface erosion. And here we see the application of coir mat to give a green finish for a landfill, where one of the longest or the largest landfills in the world that was built in Visakhapatnam. and the entire landfill was built above the ground level, and unless it is given some natural finish, it may look very ugly, and we want this entire structure to blend with the surrounding green hillocks and other features of this area. And here, by covering the entire embankment with the coir mat, we could grow the vegetation, and now it looks very green and blends with the surroundings. So, another characteristic of the natural geosynthetics that we can take good use of is the surface character, and the surface of most of the natural geosynthetics is very rough compared to their synthetic counterparts, and because of this roughness they have excellent surface interaction with the surrounding soil, and that means that they can mobilize higher reinforcement force at a lower strain, and I will illustrate that through some examples. And here at IIT Madras some students have done some tests on the use of coir geotextile similar to this similar to the one that you have here for reinforcing a soft clay, and 4 series of tests were performed. The first series, the plate load test done on clay soil alone, and the second series the clay soil with some muram soil layer, and then the third series is the plate load test with the clay plus gravel and with one basal reinforcement layer, that is at the base of the gravel, and the fourth series there are 2 layers of reinforcement, one at the base of the gravel and another at mid height of this muram soil, and let us see how they perform. And this natural geotextile, the coir geotextile, it is a relatively soft textile. It provides or it develops maximum tensile force of about 36 to 37 kilonewtons per meter at a very large strain of nearly 40%, 42%, and when it is treated with some polymer coating, we can make it stiffer. The strength has marginally increased about 43 kilonewtons per meter, and the strain at the peak load is about 16%. And the particular geotextile that we have, it is susceptible to repeated load applications, and the strength reduces from 100% to almost 55% after about 60 load applications. So, the particular product that we are dealing with is a very soft product, and this particular result was obtained by applying nearly 90% of the ultimate strength, and it is not bad that even after about 60 cycles about 55% of the strength is still remaining in the coir. And the result of these plate load tests is like this. On the x axis we have the pressure, the y axis we have the settlement, and the series 1 is the test that are performed on soft clay alone. It develops very low compressive strength of about 10 kPa, and when there is a gravel layer of 100 millimeters thick, the plate pressure increases to almost the ultimate bearing capacity or ultimate pressure increases to nearly 200 kPa, and when there is one layer of coir geotextile placed at the base of the gravel, the pressure increases slightly to about 225 or 240, but then when we provide one additional layer of geotextile at the mid height of muram, the result is phenomenal. The ultimate pressure has increased almost from about 200 to more than 500 or 550 kPa, and this particular result can be only attributed because of the excellent interaction that is taking place between the coir geotextile and the muram, and because of the rough surface it is able to hold the soil together much better, that is resulting in mobilization of the higher capacity from the soil, because ultimately the soil is the one that needs to take the load, and the coir that is provided in between the muram layer is able to hold it in place and allow it to develop a higher strength, because actually this particular geotextile is provided at a depth of 75 millimeters from the surface. That means that the overburden pressure is very nominal. In spite of that, we are able to get a very good increase in the strength of this the system, and that can only be explained by looking at the surface characteristics of this geotextile. And these are all the data with different heights of the muram soil. These are all the results obtained for the unreinforced systems, and these are from tests from series 3, that is with the basal reinforcement, and this is the result from series 4, that is with the 2 layers of reinforcement, and the ultimate pressures that were obtained are like this. When the thickness of the gravel layer is let us say about 200 millimeters, the maximum pressure that we can apply on the unreinforced system is 240 kPa, and with 1 layer of reinforcement at the base it increases to 250 kPa. It is only a marginal increase, and with 2 layers it increases to 750 kPa, and say if we have a thickness of 350 millimeters, the unreinforced system can take a maximum pressure of 400 kPa, which increases to 500 with 1 bottom layer. But then when we provide 1 additional layer, this capacity almost doubles to nearly 1150 kPa, and this shows that we need a good interaction between the reinforcement and the soil to mobilize higher capacities. And does this mean that we do not require a basal layer because we are not getting a good improvement? We should not think it like that, because the base layer also plays a very important role in preventing the intermixing of good quality muram with soft clay soil, and that can only be achieved by placing the layer at the bottom, placing the geotextile layer at the bottom of the muram soil, and that in turn helps in long term performance, whereas the reinforcement layer that is placed at mid height of this muram soil can help in the short term performance, or it can immediately develop the force and increase the capacity. And so we can think of for the long term benefit, we need to provide 1 layer of reinforcement at the base of the muram soil, and for a short term performance we require 1 additional layer of reinforcement at the mid height of this muram soil. And the same data that is given in a different form corresponding to different rut depths, and what should be the base course thickness for unreinforced system, and for with 1 layer of reinforcement at the base and with 2 layers of reinforcement. And the similar data was also published by other researchers, and one example is the paper by Rao and Sridhar that was published in 2012. They compared the performance of a coir geogrid, which is very rough like this, with a geogrid made of synthetic. The polymeric geotextile surface is very smooth like this, which has a modulus of about 52%, 52 kilonewtons per meter, and the coir geotextile it has a modulus of 16 kilonewtons per meter. This is the secant modulus at 5% strain, and the friction factor is 0.94 from the modified direct shear test, whereas for coir geotextiles it is 1.07. And they have done a lot of laboratory tests by using a compacted pond ash as the subgrade soil, and by placing the reinforcement at different depths they have done this test, and their observations are here. The bearing capacity ratio, that is the bearing capacity of the unreinforced the soil in the denominator, and the bearing capacity of the reinforced soil in the numerator, just as how we have defined in the earlier lectures. And with the different u by b, that is the u by b is at different depths the reinforcement is placed, and then the surcharge effect, because they have placed the footing at different depths to get different surcharge effects, and the bearing capacity improvement ratio is maximum with polymeric type reinforcements. Obviously, this is the result at 5% the settlement equal to 5% of the footing width, and whereas the benefit with coir is slightly better, but not as much as with the polymeric geotextile. But if we see at the ultimate state where the rutting is much higher, the coir geotextiles they have a higher bearing capacity improvement ratio as compared to the polymeric product. That is because at higher rut depths the coir geotextile is able to produce higher force because of better interaction that it has with the surrounding medium. And some of the observations is that the coir geotextile at the base of the gravel layer did not show much of performance improvement, because the surface is very smooth because of the soft clay that we have. However, this base layer can act as a good separator and filter in the long run, thus improving the performance, the long term performance. And the additional coir geotextile at mid depth of the gravel layer results in a significant improvement because of the good interfacial friction between the coir and the gravel, and hence the strength of the geotextile and also the soil is mobilized to a higher degree. So, compared to the jute fibers, the coir fibers, the jute fibers, they are more finer and they have better spinnability, and they have the jute fibers, they have higher initial strength, and the consistency is more uniform in the case of jute fibers, because these jute fibers are very long as compared to the coir fibers, and they have a higher rigidity, and they have a good roughness, and they have very low elongation at break, and they have excellent drapability. Drapability is a property that is, if you make a cloth out of these fibers and if you spread on a surface, they can take the contour of the ground more easily, that is called as the drapability. And the jute fibers also, they have the mulching property, and they create a congenial microclimate for the growth of the plants. And some comparison between the jute and other synthetic products, the specific gravity of the jute is 1.48, whereas polyester and polypropylene they have the specific gravities of 1.38 and 0.91, and the breaking strain is very interesting. And the jute, they have breaking strains of about 0.8 to 2%, whereas the polyester it has got 7 to 37%, polypropylene about 17%, and the effect of the heat is quite significant in the case of polymers, whereas the jute, it does not melt even at 180 degrees centigrade, whereas the polyester at about 180 degrees centigrade it starts sticking to the hands, and whereas the polypropylene, it softens in the range of 143 to 154 degrees centigrade. So, that means that the polypropylene and polyester type geotextiles, they may not be used as asphalt overlays, because the asphalt is placed at high temperature about 130 to 140 degrees centigrade, whereas a jute textile, because it does not melt even at 180 degrees centigrade, it may be a good product that we can use as an overlay fabric. And here we see an example of the vegetation growth after covering this area with a jute geotextile, and here we see the application of a jute geotextile being spread on a spoil heap mine dump to promote the growth of vegetation. And another form of natural product is the bamboo, and recently there were some studies on the use of bamboo as a reinforcement, and here we see tensile testing of a bamboo geonet, and here we see a tube that is made of bamboo net, and this picture shows the reinforcement of a soft clay soil using a bamboo grid that is filled with stones, and this is similar to geosynthetic encased stone columns. Here we have a bamboo net that is encasing the stone column to improve its performance, and the tensile properties of this bamboo geogrid, at about 5% strain, it develops a force of about 110 kilonewtons per meter, and it is a fairly good strength developed at a relatively low strain, and the result of encasement is quite substantial. This is the pressure settlement data for clay soil alone, and this is with ordinary stone column, and when the entire stone column is encased in a polyester geogrid, this is the type of response that we have, and if it is encased in a full length bamboo encasement, there is a substantial increase in the pressure capacity, and we see that both the initial slope and the ultimate pressure, they have increased by using the bamboo geonet reinforcement, and here we see the comparison with the different lengths of treatment. Sometimes we may not require the treatment of the stone column for the entire height. Actually, this is the full length encasement, whereas with encasement over a length of 2 times the diameter, this is the type of response that we have, and 3.5 times the diameter, this is the response that we have. So, that means that even bamboo reinforcement can increase the stone column capacity, and wherever we need the stone column support for a limited period, then we can utilize the bamboo as a possible encasement to improve our stone column stiffness and also the ultimate load capacity. And just to conclude, our geosynthetics can help in sustainability in several manners, as we have seen earlier, and the natural geosynthetics can play an important role in engineered structures, and the moisture holding capacity and the surface roughness of the natural geosynthetics are highly beneficial properties for successful applications, not only in the reinforcement applications and also in the surface erosion control applications. And the natural geosynthetics can be applied in erosion control works, drainage, and in PVD applications, and their limited strength can be used in non-critical applications such as in low volume rural roads and other erosion control works. Okay. So, thank you very much.